So last few days here, guys, we've been working on the work energy theorem. Okay, we've been looking at the formula that says that work causes a change in mechanical energy. Okay, either kinetic energy or potential energy, and we worked on some problem-solving stuff to do with that yesterday. Okay, today what we're going to be focused on is the formula that actually calculates work, and that's force times distance. Okay, so the lab today will be investigating the relationship between force, distance, and work. Okay, so what we'll be doing, okay, is essentially measuring the amount of force that is needed to stretch a rubber band certain distances. Okay, so we, as the experimenter, are selecting the distances. We will be measuring the responding forces that will result from those distances. Now, the setup for this experiment is going to go as you see in the picture there. You're going to have two desks, and you're going to space them so that the feet are a certain distance apart. Now, what you'll have to do with this is that it does have to be two different desks, and you're going to want to use like the two back legs. So I would take these two desks, okay, and set them so that I've got the legs a little ways apart. Not very far, because our rubber bands are not that big. Okay, we only need them to go around the legs and be taut. Okay, not overly stretched, just so they're not loose. Okay, everybody with me on that? All right, so that's how far apart you need to put the legs. Then you need to have two group members whose only job is to make sure the desks don't move. That is, they need to sit in the desks so that they don't move while you do the experiment. If they move, you will change the amount of tension that's in the rubber band to start with, which means it'll take more force after that to stretch the rubber band than it should have. Everyone with me there? So we have to make sure that the conditions affecting the rubber band stay the same throughout the entire lab. That is, the desk legs stay the same distance apart. There's the same amount of tension in the rubber band, okay, until we start pulling it. Right? So it's absolutely crucial that the desks do not move. So what we'll be measuring, okay, is we'll have a ruler on the floor to help us measure our distances. The distances, like we said, are already selected for us. Okay? So we'll just have the meter stick sitting on the floor, okay, so that the end of it is right between the two pieces of rubber band, right? Because we're actually going to pull both sides of the rubber band at the same time. Okay, we're not just going to pull one side, we're going to pull both, just like they show in the diagram here. All right, so we'll pull to those distances, and we will measure how much force is required using our spring scale. Okay, that's what this little device here is. Now, the problem with these spring scales is this. They don't have force on them. They're supposed to. The box they come in shows a picture of a scale that has force in newtons on it. So when we ordered these and they came, we're like, sweet, they're here. And then we pulled them out, and the ones we got have grams and ounces on them. Not that big a deal. We tried to return them, but they wouldn't take them back. We're like, customer's always right. They're like, hell no. So anyway, we never bought anything from them again. But anyway, it'll work, okay? All we have to do is take what it reads in grams and divide it by 100. That'll be our force in newtons. It's not exact, but it'll be close enough for what we're doing, okay? So if it reads 400 grams, it's 4 newtons, okay? Easy conversion, right? But that's what we'll be measuring, okay? And we'll be using the spring scale to do that. Now, we need to make sure that when we're doing our measurements with the distance, that we are looking straight down on the ruler. Okay, we don't want to bring any angles in, because then you have something called parallax, which means when you're looking at an angle, you may not read it correctly. Okay, so we want to make sure that you've got a group member who's looking down from the top while pulling on the spring scale. Okay, so you pull it to the certain distance, and then you record the reading on the face of the scale. Okay, pretty straightforward procedure. That's all there is to it. Pull it to the distances, record the reading on the scale. That's it. It'll take you no time at all to do the procedure. Okay. Now, there are two different kinds of scales in the box. Okay. There are 500 gram scales and there are 2,000 gram scales. You need a 2,000 gram scale. Right. If you take a 500, they're green, not red, and you'll max them out right away. Okay, you'll pull them to the end of the spring and not be able to read anything. So you need the 2,000 gram spring scales for this. Okay, our distances, okay, if you've got your file open right now, our distances are in meters, 0, obviously, okay, 0.05 meters or 5 centimeters, 10 centimeters, 15, 20, 25, and 30, okay. So those will be the distances to which we pull, and we'll be measuring the force to those. All right, so the problem we're investigating here, guys, is how can we determine the amount of work done, okay, on on an object or system. Okay, so we've got our variables. We've kind of talked about those. Okay, for our hypothesis, okay, what we want here is obviously an if, and then statement. Okay, the if part needs to tell me what work is. Okay, so kind of a definition of work. Okay, the and part describes the experiment as always. Okay, the then part, I would like you to explain to me how you will calculate the work done, okay, on the object using a force distance graph, okay, which you will build in Google Sheets. Okay, I did not attach a Google Sheet this time. You can make your own. It's not that hard. Okay. Now, the good news about how to calculate work from the force distance graph is that it may sort of tell you that in the procedure somewhere, right? You would just have to, in the analysis, kind of explain why that worked. All right, so we got it. We talked about our hypothesis. We talked about our procedure. Okay, for the analysis and interpretation. Okay, they say they want you to calculate the area beneath the line on your force distance graph. Okay, the best way to do that would be your 1/2 the base times the height. I would ignore this part about half the maximum force exerted by the distance moved. Okay, just do the half the base times height. Okay, and you'll be able to go from there. Okay. Then for question number 2, it's asking you what the area under a force distance graph represents. How do you know? Okay, so when you're looking at this graph here and you calculate the area, I want you to think about what things you're putting together when you do that. Okay, because to calculate the area of a triangle, you go 1/2 base times height. Okay, I want you to think about what you're multiplying when you multiply the base times the height. Kind of giving you the answer there. Okay, all right, just explain and maybe talk about what units you might get for that. Okay, kind of as a justification of I calculated this when I did that. Okay. Then conclusion, same as always, restate your hypothesis, explain why you can accept or reject it. Okay, and then your sources of error. Okay, should be able to come up with a few on that. One thing to note, I would like the rubber bands back when we're done. Okay, they are not a toy. You don't want anyone to lose an eye. Okay? And if your rubber band breaks in the middle of your trials, what will you have to do? You'll have to get a new one and you'll have to start over. Okay? Because you'll have to move the desks. It'll be a different rubber band. I mean, the rubber bands should be about the same. They're all the same in terms of their strength, but because you'll move the desk legs and you require that consistency, you'll have to start the trials over again, which shouldn't take you too long, and rarely do any of them break, okay? Just in case one has a flaw in it and it snaps. Okay? Yeah, well, you shouldn't, but all right. Any questions on what we're doing? Okay, if there's questions while the lab's going on, feel free to ask. You're gonna need at least 3 people in your group, probably 4, okay? Just because you need 2 people sitting in the desks all the time just to hold the desks in place. Okay. All right, have at her. You should be able to get this lab report pretty much done in class today, but I didn't make it due till next Thursday.